In this video, we're going to take a look at modified Atwood's machine problems with friction. Let's start with this one. A 3 kilogram mass is attached to a hanging mass H by a rope as shown below. You add more and more mass until the system just begins to move when H is equal to 2 kilograms. What is the static coefficient of friction? Okay, so in this problem, the first thing is to realize when it just begins to move. That's telling us that we're taking a look at a static friction problem, which the static coefficient of friction being what we want to find, that should kind of be a dead giveaway. And when you think about this, it is going to move. The 3 kilogram block is going to move, but it wants us to think about that last moment when it is still at rest. So for this problem, the acceleration is still going to be 0, and all of the forces are going to be balanced on each object. So the 3 kilogram block, it's going to have tension to the right, and then also some friction between the surface acting back, which we are going to call Fs. And the idea here is that static friction force, the maximum, we can call that F max, is equal to the tension at that last moment when H equals 2 kilograms. Okay, then I think about this block, the hanging mass, and I know the tension T is going to be equal to the weight. We'll call this mH, the mass of H, times G. And again, at that last moment before it begins to move, the tension and the weight, they're going to be equal. So basically, this is just a fancy way of trying to say F max equals tension, and tension equals the hanging mass. So the maximum static force of friction is equal to the mass of the hanging mass times the acceleration due to gravity, or the weight of that 2 kilograms. Okay, so to figure out what mu s is, I'm going to take the force of friction and divide it by the normal force, right? Because friction, a good way to remember this is friction is fun. It's always mu times normal force, and in this case, s, mu s, and we would be looking at the max value. So mu s is equal to that maximum static friction over the normal force. Now, in this case, I'm taking a look at the normal force of the 3 kilogram object. So I would need to say, we can call this thing like MA if you want, times G. And the normal force is equal to that. So you would have F's max, mass of the hanger, times acceleration due to gravity, and then for the normal force, you would have the weight of the 3 kilogram block, or MA, over G. Now, the reason why we kind of wanted to write it this way is because now I can see the acceleration due to gravity G, it cancels out, and really the coefficient of friction is just a ratio of the masses, with the hanging mass on top, 2 kilograms, and then the mass of the block on the table, A, which is 3 kilograms. So 2/3 or 0.6 forever. And there's no unit because the kilograms cancel out. Okay, great. So that's the maximum static coefficient of friction. Let's try another problem. A 5 kilogram mass is attached to a 3 kilogram hanging mass by a rope as shown below. Once the system is set in motion, the blocks move with a constant speed. Okay, constant speed. Oh my God, constant speed, constant speed. Every time you see constant speed, circle it, underline it, star it. That is the most important thing that a problem could ever tell you. So constant speed, what does that mean? Well, again, just like in the last problem, the acceleration is 0. And automatically, I know that all the forces are balanced. So even though this 5 kilogram block is going to move to the right and the 3 kilogram block is going to move, have a velocity down, that's a constant velocity, and the acceleration is still 0, so the forces are balanced. Okay, so what does that mean? Well, before I even get into what it's asking me to find, I'm just going to think about the forces acting on each object. I've got tension acting to the right on the 5 kilogram block, the force of friction. In this case, it's going to be kinetic because there is still movement. And I know that friction and tension, those two are equal. Then we've got the weight of this object. I'll call this thing A and the other one B, just to make it easy for myself. So MAG is the weight, and then the normal force is up. And it's important for me to notice that the normal force is equal to MAG. All right, now let's look at the 3 kilogram block. The tension acts up, and again, it's moving down, but with a constant velocity, so that means the tension is actually equal to the weight force. Now, similar to before, this is telling me that the kinetic force of friction is equal to tension, which is equal to the weight. So I know Fk is equal to the weight of that hanging block when it's moving with a constant speed. Okay, so I also know that friction is fun, so mu k times the normal force. And here's where we get to part A. Part A wants me to find the kinetic coefficient of friction. So that's this guy right here. It's pretty obvious what I would do. I would say mbg equals mu k over n, and let's remember that this normal force is actually equal to m a times g. So m a times g. And now notice again, the acceleration due to gravity cancels out, and when I want to find mu k, I'm just going to divide both sides by the mass of A, and exactly like in the last problem, I get that the kinetic coefficient of friction is the ratio of the hanging mass over the mass on the top of the table. So mu k is going to be 3 kilograms, which is the mass of the thing that's hanging, and then divide that by 5 kilograms. Okay, so that gives me a kinetic coefficient of friction of 0.6, not 0.6 repeating. And again, the kilograms cancel out, so the mu is unitless. Okay, so that's part A. Part B changes things up. It says if you add 2 kilograms to the hanging mass, what will be the tension in the rope? Okay, so basically I'm going to restart the problem and forget about the idea of constant speed, because once you put 2 kilograms on top of that block, now the tension is going to be larger than, not that way. It's going to be larger than the force of friction, and it's going to accelerate. So, well, does anything stay the same? Yes. The coefficient of kinetic friction isn't going to change. So as long as it's the same block on top, the 5 kilogram block, then that coefficient of friction will still be 0.6. So I'm going to save that. I'm going to write it up here. Mu k equals 0.6. And then I'm going to erase a bunch of this work so we can start fresh. Okay, here we go. Fresh start. So now, instead of just having 3 kilograms, we're adding a 2 kilogram block on top. Now, what I'm going to do is I'm going to change my mass B from 3 to 5 kilograms and just pretend like it's one object. So MA is 5, and now so is MB. Okay, so what do we do to find the tension in the rope? Well, this is going to be a problem where we write a system of equations, cancel out the tension, find the acceleration, then plug that back into one of our equations to find what the tension is. So the forces are going to be very similar to what we had before. Let's start with the 5 kilogram block. And you know what, let's do the weight and the normal force first. Obviously, the weight, call this MAG, is still equal to that normal force. But now the tension in the rope, T, is going to be bigger than the force of friction I should kind of draw the force of friction, or the tension short, because I don't have a lot of room here. Okay, so tension is going to be bigger than the force of friction because it's accelerating to the right, and I would still label this kinetic, FK, kinetic friction. Okay, then that tension in the rope, T, those are still equal. Because remember, tension on either side of the pulley is equal as long as the pulley is ideal and it doesn't have mass. But because we've added mass to the hanging block, now the weight force, MBG, is bigger than the tension, and it unbalances it, and it causes the system to accelerate down. So I'm going to write this positive A, and remember we use our direction of acceleration to decide whether something should be positive or negative in our system of equations. So let's work on that system of equations. Let's start with A. I'm going to have T being positive, then subtract Fk, or friction. And that will be equal to the mass of A times the acceleration. So remember, these are both equations of net force. This one comes from the free body diagram. This is always true. Mass times acceleration is always true. Okay, now let's take a look at B. For B, I have MBG as my positive force because it's going down, and T is now a negative force because it's going up in the opposite direction of the acceleration. Okay, and then when we set these two things equal to, we'll write mass of B times the acceleration. Again, these are the net force equations for B that we're getting. Okay, so I have my system of equations. Now I'm going to add both the left and the right sides to eliminate tension. And I'll get MBG minus kinetic friction equals MAA plus MBA. And of course, I want to find the acceleration. So that means I'm going to need to add, or factor out, sorry, the acceleration. So I have MA plus MB. Okay, and then finding the acceleration means I divide both sides by MA plus MB, right? So the whole term goes away. Okay, so now I have my acceleration equation. There's one last thing that I need to do. Here, I'll write it over here so that I have a little more room. I've got MBG minus FK for friction over the sum of MA plus MB. And that's it. I still need to figure out what the kinetic friction is. So to do that, we use the same equation as before. Friction is fun, so mu k times n. But remember, n is actually mag, so I can write this mu k mag. And I would put that inside of my equation for friction. So that's what I would put here. I would write mu k mag. And then I would, plug in my numbers and chug away. But of course, if I wanted to, in this problem, I could factor out g, and I'd have mb minus mu k ma, but it's nitpicky. So what is the acceleration going to be? Well, I've got mb times g, so 5 times 10, 50 newtons, minus 0.6 times mag, which ma is 5, so that's 50 newtons, all divided by ma plus mb, so 10. Okay, so 0.6 times 50 is 30. So 50 newtons minus 30 newtons divided by 10 is 2 meters per second squared. So the acceleration is 2 meters per second squared. We're almost done. What do I do with that acceleration? Well, now I can plug it back into either of these two original equations to find the tension. So I'm going to get rid of some of this work here. And just pick an equation that I want to plug the acceleration back into. I'm going to use the top one right here. So I would write this T equals ma times the acceleration plus friction, which, remember, friction is mu k mag, and that's that 30 newtons that we calculated. So I would do the mass of A, 5 kilograms times 2 meters per second squared, plus, we already calculated this, is 30 newtons. So 10 newtons plus 30 newtons, or 40 newtons, is the tension between them. Woo. Let's do one more. Oh, this one's going to be rough. A box of mass M1 is attached to a box of mass M2 as shown below. M1 is 10 kilograms and M2 is unknown. Let me rewrite that so I do not forget. 10 kilograms, M2, big old question mark. The coefficient of kinetic friction between M1 and the table is 0.5. Okay, kinetic friction, good to know. Using a ruler and a stopwatch, you measure M2 falls 0.4 meters in 0.4 seconds. Ooh, okay. When released from rest. Motion. This has got motion information. Ooh, okay. So the initial velocity, v naught, 0. The initial height, we'll say, is 0.4. And then the final height that it reaches, we'll call that 0, right? It'll be down here. That way it falls that 0.4. Oh, you know what, though? This problem is going to be tricky because it falls down, and that's going to be the positive direction of acceleration. So let's decide the initial height is 0, and it ends not at negative 0.4, but at 0.4 meters, because down is going to be positive on this side. Okay. And the time that it gives me is 0.4 seconds. Before I do anything, I'm going to recognize that it has given me enough motion information to solve for the acceleration, which is a very useful quantity in these problems. So what equation am I going to use? Well, I look at my motion equations and I think about what has y naught, a, t, and it's this equation. Now, notice I'm not modifying this to use like negative g or anything, because the acceleration is not going to be the acceleration due to gravity. It's going to be a very specific acceleration that we get from this problem. So I get rid of anything that's 0. The initial velocity is 0. We're saying the initial height is 0, so those are bye-byes. And I want the acceleration, which means I multiply both sides by 2. Then divide both sides by time squared. So the acceleration is 2 times 0.4 over 0.4 seconds squared. Okay, so 0.8 divided by 0.4 times 0.4 is 5. Like the whole thing is 5 meters per second squared. Okay, so that's the acceleration. I'm going to write that up here and save it, then continue working on the problem. Okay, now let's address the big question. What is the mass of M2? Okay, so clearly this thing is going to accelerate, and we know that the acceleration is 5 meters per second squared, and it's down for M2, and left for M1. So we're going to do our normal process. We're going to write we're going to draw free body diagrams, and then we're going to write systems of equations and see if we can figure out how to get M2 by itself. So let's start with M1. I'm going to have M1 times G as the weight, and the normal force up is equal, so N equals M1G. Okay, then there's tension to the left T, and there's going to be some kinetic friction, Fk, to the right. The tension will be bigger than the friction, and you know what? We had to do this last time. The friction is going to be mu times the normal force, which is the weight. So let's just go ahead and write this, mu k times m1g. Okay, so that's the force of friction. Now for m2, it's going to have tension up and the weight, m2 times g down. Okay, so let's write our system of equations. What are we going to get from this? Well, starting with m1, remember we decided that left is positive because that's the direction of the acceleration, so I would make t positive, then subtract fk, which, I'm going to go ahead and write that as mu k m1g, just because I already wrote it down, and I'm pretty sure I'm going to have to do that. Okay, so tension minus friction is equal to what? It's equal to the mass of 1 times the acceleration. So that's our first equation. Okay, then I look at m2. Now I have m2g as the positive force, because it's in the direction of the acceleration, and I subtract tension. Okay, then this is equal to the mass of 2 times the acceleration. So how am I going to find m2? Well, I don't know tension, and that is a clue that we need to add these together so we eliminate tension. I'm going to get m2g minus friction, or mu k m1g, equals m1a plus m2a. Okay, so now here is a problem where I know what the acceleration is and I don't know what a mass is. So I'm not going to take this and factor out the acceleration so that I get m1 plus m2 times acceleration. Instead, what I'm going to do is I'm going to try and get these two terms with m2 on the same side as each other. So I'm going to subtract m2a from both sides, so I get m2g minus m2a, and then add friction over to the right. So I get m1a plus mu k m1g. Now on the left side, I can factor out m2. I'll have m2 times g minus a. And I can take this g minus a and divide the left and the right side by it. So let me put this over here. I'm going to get m2 equals m1a plus mu k m1g, and then I'm dividing the whole thing by g minus a. So what is this going to give me? Well, remember m1 is 10 kilograms, so 10 kilograms times the acceleration, 5 meters per second squared, plus mu was 0.5 times 10 kilograms times the acceleration due to gravity. We'll use 10 meters per second squared. Divide that whole thing by g, 10 meters per second squared, minus a, 5 meters per second squared. Whew. So just a big old nasty equation. 10 times 5 is 50, right? And 0.5 times 10 times 10 is 50, so 50 plus 50 is 100. And then I divide that by 10 minus 5, which is 5, so that gives me 20 kilograms for M2. Dang. This was a super tough problem, and this is something that if you were asked to do this on like the AP test, it would be an entire free response question, and you would have 15 minutes to get as much of it done as you can, and you would not have to get all of it done to get enough points to pass or get a 5. Anyway, this video is over.